In example 5 and the later examples in this chapter, we're just going to repeat what we did in the previous problem. So the work is going to be very, very similar. The function is going to be different though. So in part 1, we have a function f of x. In this case, it has x minus 2 to the power of 2/3 plus a 1 on the outside. And they're asking for the critical numbers again, so I need to know what the derivative is. And in this case, to find the derivative, I would have to use the chain rule, or in other terms, the extended power rule. So bring the power down, then subtract 1 from the power, and you get negative 1/3, and then multiply by the derivative of the inside. The derivative of x minus 2 is going to be 1, and that's the end of that. Now I want the derivative of 1, which is going to be 0. So you know what? I'm just not going to write it down. So let's just get rid of it. Now, having a negative exponent is a kind of a bad thing, so I'm just going to rewrite this expression with the 2 on the numerator, the 3 on the denominator, and then the x minus 2 with the power 1/3 down on the denominator, and then making the exponent positive. So instead of having a negative 1/3, I'm going to make it a positive 1/3. And keep in mind that when you have a to the power of m divided by n, that's the same thing as the nth root of a to the power of m. So I'm going to rewrite my derivative as a radical expression just to be able to make a little bit more sense of it. So 2 to the 3 are there, and then the radical, and then we have x minus 2 on the inside. And keep in mind that in this case, the index is 3, so that's going to go on the outside, and the power is 1. And so you can write down x minus 2 to the power of 1, but it's kind of silly. I'm just not going to write down the 1. I'm just going to leave it as x minus 2. So that's my derivative. And now the question is, what makes the derivative equal to 0? And for this problem, the derivative can never ever be equal to 0. For a fraction to be 0, the top needs to be 0. And in this case, the top of the fraction is 2, and that can never change. It's always going to be a 2 no matter what. So the derivative can never be equal to 0. However, can the derivative be undefined? Can f prime of x be undefined? And in this case, the answer is yes, it can be undefined. This is actually going to happen when the cube root of x minus 2 itself is going to be 0. Again, the 3 is always going to be 3 no matter what, so we can just ignore it. But the radical could be equal to 0, and that actually happens when the inside of the radical itself is equal to 0. When x minus 2 itself is 0, the cube root of 0 will be 0. So that means that the critical number is going to be the number 2. So that's basically the end of that part of the problem. At this point in time, I'm going to figure out where the open intervals where the function is increasing and decreasing are. So in order to do that, I'm going to draw my horizontal line and put the critical numbers on it, and then figure out which one is going to be a positive value, which one is going to be a negative value. So you know what, let me do this again. I'll just extend the line a little bit further out and move it. And this is the function f prime of x that's being tested. Here's negative infinity, here's positive infinity, and the critical value in this case was 2. So I need to pick a number before and a number after. I'm gonna pick 0, and I'm gonna pick 8, let's say, or 10, or whatever. It doesn't really matter. And what I'm gonna do is take those numbers and put them into the derivative. Remember, this is the derivative, so when you plug in 0 in there, the answer that you get is going to be a negative value eventually. So once you determine that, you can pretty much get rid of the 0 and just leave the minus sign. However, when you plug in 8 into the derivative, so take 8 and plug it in, and you can use a calculator for this, it's not a problem, you will notice that the answer you get on your screen is going to be a positive amount. And so that means the derivative is going to be positive. Now, having a derivative that is negative and then positive means that the function f of x is going to be going down, then the function f of x is going to go up. And so that means that 2 itself is going to be labeled as a minimum later on. Before I move on, let me show you what this looks like on a calculator. So my goal is to plug the function f of x into the calculator and show you what the graph looks like, so we know that what we did is actually correct. in order to do that, I'm going to turn it on and go to the Y menu. So click on the Y and then clear whatever equations you've got, and then type in the equation in this problem, which is x minus 2 all to the power of 2/3. So my calculator puts me in the power right away. I'll show you what it looks like if it doesn't put you in the power. So then plus 1. So that's my function. Now it's saved, and I'm going to click on graph, and you'll see that at 2, if you trace the value 2, you'll notice that there's a low point. The rest of the graph is always higher than this. So 2 is a minimum, which is what we discovered when we did the work down here anyway. If you have a calculator that's not super user-friendly, it's going to look like this when you type it in. So you're just going to go x minus 2 again, and then you're going to put an exponent. So that little arrow key means exponent. But in this case, the exponent has a fraction. So make sure you use parentheses. Otherwise, the calculator will not understand what you're trying to type in. So that tells the calculator that the 2/3 is now in the power, and then plus the 1 on the outside. And then just click graph again, and you'll see the same exact picture that I had. So same deal. And then when I trace 2, you'll see that it's a low point. And so that's pretty much it. That's what I want to show you on the calculator. Notice how the calculator is saying that the y is equal to 1 there. Remember, the derivative is equal to 0, but the function is equal to 1. So if I plug in 2 into the expression that we have up here, into the equation of the function, your answer will be 1. That's what this means. So back to what we have over here, and in the second part of the problem, they want to know where the function is increasing and decreasing. So let's write it down. So f of x is increasing on the interval from 2 all the way to infinity. That's the second part. And it's decreasing on the first interval. So it's decreasing on the interval from negative infinity to positive 2. And in part 3, they wanted the relative max and mins. Actually, in this case, there's only one minimum. And in this case, you can actually call it an absolute if you wanted to. That's because it is literally the lowest point ever on the whole graph. And that's pretty much the end of parts 2 and 3. Finally, part 4, which was to graph the function. So let's see if we can make an xy plane. And the number 2 is the one that's interesting in this case. The number 2 on the x-axis gives us a minimum. And we discovered on the calculator that the minimum was 1. And the graph pretty much looked like this. So that's what the function f of x looks like in this particular example. So awesome. How did they get the 1? Again, if you don't remember how to get the 1, you get the 1 by putting the 2 into the function. Why are we putting 2 into the function? Because 2 is the critical number. We put it into the regular f of x to get the y coordinate. If you put it in the derivative, you're going to get undefined or 0. So be careful about that.